In this video, we present our work on super resolution and high dynamic range from a burst of raw images shot with an handheld camera. We shot this scene by night in a low light setting with an handheld phone camera. Although it might look okay at this resolution, closer inspection reveals digital camera sensor flaws, such as saturations next to the statue. Besides, the text and details of the statues on the right are barely visible because of poor spatial resolution and noise. Our method aims at recovering finer resolution and increasing the dynamic range. We show here examples of reconstruction with our method. Notice that the text is perfectly visible. Large amounts of details are recovered on the statues and stained glass. Here is a second challenging example. This scene has a very large dynamic. Information is lost around the light bubble, and most of the low light background is not visible due to the noise. Our algorithm successfully reconstructs the scene, and closer inspection reveals more details. Writings are now visible in the open book and on the bottle in the background. Noise is reduced on the computer screen and on the table on the right. We now detail the image formation model of the camera that will be used for reconstructions. In our presentation, we restrict our attention to the raw images captured by the sensor. A reasonable model is to consider that the raw pixel value linearly corresponds to the amount of photons captured. In this example, the more photons are collected, the brighter the pixel value. Full well means white color. The raw linear measurements are impacted by various sources of noise at the different stages of the image acquisition pipeline. For instance, shot noise is due to the random arrival of photons on the sensor plane, which is a physical properties of photons. Readout noise comes from the electronic and the amplifiers. Quantization noise is caused by the analog to digital conversion. The nature of noise resulting from different sources depends both on the scene and the camera. A first consequence of the noise is that the smallest meaningful signal that can be recorded is just above a threshold called the noise floor. For instance, in the image on the right, the background is totally lost. While on the other hand, if the photosite is saturated, any new information is lost. The light bulb is not visible due to this saturation effect. The dynamic range is the ratio between the saturation level and the noise floor. Our goal is to increase the dynamic range beyond the limits of the sensor. We can do so with image bracketing. Image bracketing consists in taking photographs of the same scene with different exposures. For instance, the light bulb is well exposed in the first frame, but is saturated in the other ones. The table is well exposed in the middle frame, and the background is well exposed in the last frame. Bracketing consists in fusing the regions that are well exposed in each image. For instance, this image has a large dynamic range since it features a light bulb and a pitch black area. The resulting image merges the correct regions of each frames and shows details for all the regions. We now focus on the second limit of the sensor, which is spatial resolution. Spatial resolution is another limit defined by the sensor. An efficient way to improve the resolution of the image is to leverage aliasing. High-frequency details above the resolution of the sensor will result in low-frequency artifacts in the low-resolution frames. For instance, notice the varying colored artifacts on the metallic grid across various frames caused by hand tremor. These artifacts from several frames can be used to successfully reconstruct the high-frequency image on the right. Because both HDR and super resolution rely on combining multiple frames, We jointly address these two problems by leveraging at the same time aliasing and exposure bracketing. We take with an handheld camera a burst of bracketed low-resolution images. Our algorithm produces a high-quality output with higher resolution, larger dynamic, and better signal-to-noise ratio. Now, considering this night scene, we show a close-up detail and the various frames composing the burst. This shows an important challenge addressed by our method. In order to perform high-quality super resolution, we must align images with different expositions. However, this is very challenging because the SNRs are not consistent throughout the frames. And this second example highlights the fact that beside varying SNRs, saturations may also severely alter registration. Nevertheless, our algorithm can make a denoised, non-saturated, and high-resolution image, such as the carvings in the red box on the right. Our model is based on an hybrid paradigm that combines classical optimization and machine learning. Our approach is based on a classical image formation model. The low-resolution frames, YK, are obtained as follows. X is an ideal high-quality image that is exposed to the camera for a time delta k, then warped with the operator WPK, blurred by the lens and the sensor integration, modeled by B, and finally decimation by the color filter array and the sensor low resolution. S is saturation nonlinearity, and epsilon models the noise. A standard way to tackle the reconstruction problem is to minimize the following penalized energy, which consists in a data fidelity term, leveraging the forward model above, and a prior, favoring natural images. Following the common and successful strategy in image processing, we parameterize the prior with a convolutional neural network, with parameter theta. In this framework, finding a solution to this problem turns down to evaluating a function f theta, which will be explained in the next slide. This parameter is learned with some training data consisting in realistic synthetic bursts and corresponding ground truths. Now we present the main steps of our method. First, given a burst of low-resolution images, we filter the images with a lightweight neural network to output a single-channel feature map per image. Then these feature maps are registered with respect to reference frame using a differentiable registration algorithm based on the parametric Lucas-Canade algorithm. Then the frames are warped according to the estimated motion vector and fused to produce a first coarse estimate of the restored patch. The motion parameters are also used to estimate some deghosting mask with a second neural network, in order to reject pixels which are misaligned, for example due to non-rigid motions in the scene or because of parallax. The final image is obtained by alternating between optimization steps on the smooth part of the energy being minimized and evaluating a CNN accounting for the image prior. In addition to the several HDR plus super resolution results we have previously shown, we present in this section additional interesting experiments and comparisons with other methods. First, we take a closer look at the raw burst super resolution without HDR enabled, because this is the closest setting where we can compare with others. We first look at this scene shot with an handheld smartphone. We zoom in the red highlighted region. We compare our method to some pure state-of-the-art deep learning-based methods. Here, we managed to reconstruct an artifact-free metallic fence. In this particular example, we also observe some remaining artifacts for the other concurrent methods. Now, we take a look at an image shot indoor with a top-of-the-line hybrid camera, with very high ISO and short exposure time in order to mitigate motion blur. If we zoom in on the bottle, we see that all the methods can significantly improve the signal-to-noise ratio and the resolution. In this example, Leo and collaborators and us are the best performers over BAT and collaborators. We benchmarked the latency, GPU memory, and model size for the compared methods to produce a 192 megapixel image from the 14 low-resolution frames. In contrast to the pure neural network approaches of BAT and Leo, our hybrid strategy greatly relies on the image formation model. As a result, a lighter CNN is in the same accuracy ballpark as the competitors, yet for a fraction of runtime and memory usage. Another important aspect is the robustness to non-rigid motion. In the case of this running person, the compared methods exhibit motion artifacts. The pure deep learning method proposed by Leo and collaborators, which showed good reconstruction quality on static scenes, now exhibits artifacts. An hybrid method for the same task also fails at predicting the correct high-resolution frame. Our method is robust to the non-static motions. This highlights the importance of the learned deghosting masks. Now we provide a comparison of two typical total variation priors to showcase the effectiveness of the CNN-based prior. The TVL2 boils down to a simple regularized frame averaging, whereas TVL1 adds a nonlinear hot thresholding module to the solver. Likewise, our CNN may also be seen as a nonlinear module throughout optimization. The variant of the algorithm with the CNN achieves by a large margin the best visual results. Notice, for instance, the face or the dress of the statue, which are more detailed and less pixelized. Finally, here we show some results of our method with various upsampling factors. We see in this example that we can restore meaningful details up to ×4 resolution factor. Solely relying on aliasing leads up to ×2 zoom. The prior pushes that limit up to ×4 in this example. Note that this is not always the case, based on the quality of alignment and the type of patterns to be reconstructed. In conclusion, we demonstrated good reconstruction up to ×4 scale factor with handheld cameras for scenes with a large dynamic range. Our algorithm is robust to low light noise and moderate object motions. The combination of model-based methods and learning-based techniques allow the use of some very lightweight models with low latency and memory consumption, suitable for implementation on mobile devices.